Okay, VSEPR theory. We say VSEPR because otherwise it's impossible to pronounce, but it is VSEPR. And those letters stands for valence shell electron pair repulsion theory. So this is based on the idea that electron pairs repel each other. It's a very simple model to predict molecular shapes. It doesn't work all the time, but it works a lot, and it's relatively easy to understand. So first we need to talk about what is an electron group. So for electron group, that could be a lone pair of electrons, a single bond, a double bond, a triple bond, or a single electron if you're dealing with a radical. So just very important here, a double bond has two pairs of electrons in it, but a double bond is one electron group, okay? One electron group. The idea here is that these electron groups around the central atom repel each other, and so like here where we have bonding electrons, that's going to affect the geometry, the shape of the molecule. So we're looking at repulsions on the interior atoms. We don't care about the lone pairs or anything on these atoms that are attached to it. So preferred geometry is going to have a maximum separation of those repulsive things, because that's a minimum energy. So let's look at beryllium chloride, and we need the Lewis structure. We've done a lot of drawing of Lewis structures, so I'm not going to go through the Lewis structures in detail here. So there's the Lewis structure for beryllium chloride. What looks wrong about that? Beryllium doesn't have an octet. But that's okay for beryllium. Beryllium and boron, along with hydrogen and helium, little stinkers, right? Why don't we see lithium in compounds like this with incomplete octets?
Because of the free charge of the nucleus?
Well, because actually it bothers me a little to see beryllium here, because isn't beryllium a metal? Shouldn't this be an ionic compound? But if you look at metallic trends, beryllium is less metallic than lithium. I think that's why we never see lithium in here. Anyway, that was just a squirrel. Here is the Lewis structure for beryllium. All of this VSEPR theory stuff is based on looking at Lewis structures. So how many groups of electrons are around the central atom? 2. So then we think, well, how could two things get away from each other? So balloons are great for this. That's why I brought balloons. We tie two balloons together. They're going to naturally go to opposite sides of the place they're tied together. Okay, like this. You'd also think about this is you and this is your ex. It just really was horrible to you. And here's the planet, and you're on one side of the planet, or let's say your ex is on one side of the planet. Where would you like to be? On the other side, as far away as physically possible, right? That's what the balloons do. So for this molecule, it arranges itself like this. These electron groups repel each other. The farthest away they can get from each other is 180 degrees of separation. That forms a line with these three atoms. And so this is called a linear geometry. Let's look at carbon dioxide. Okay, again, we have to look at the Lewis structure. So the Lewis structure for carbon dioxide looks like this. Carbon has a double bond with oxygen on each side. Looking at that central atom, how many electron groups? 2. A double bond is one group. So we have one group, two groups. Same thing happens. They're going to be on opposite sides of the central atom, also a linear geometry. The bond angle here is 180 degrees. Look at BF3. I should count how many times I've done that. That's dumb. If you draw the Lewis structure wrong, you might get your shape wrong. That's the Lewis structure for BF3. Again, this is an incomplete octet, but it's okay here because it's boron.
So boron and beryllium are happy with 2 or 3 bonds?
Boron and beryllium are happy with incomplete octets. And the way you can tell if that's going to be okay is to do formal charges. If you calculate the formal charges here, they're all 0. If you try to give beryllium an octet, then we get formal charges. Yeah, and so that's not as good. So how many groups around the central atom? 3. 3 single bonds. So if we take our 2 balloons that are tied together and we add a third, that's going to change the angles. Blast.
Wow. You hear that in movies.
Usually I say shoot or darn.
Shooter dog.
It's my parents' fault. My father was a minister.
Oh.
Okay. See what the balloons did? So before the orange and the yellow were opposite each other. Now the green one's coming in here and it's pushing these together. Okay. So that's going to make this shape. These are now separated by 120 degrees instead of 180. And if we connect the points of this, we have a triangle. You see the triangle? So this is called a trigonal planar geometry because it makes a triangle and it's flat. See that? Maybe you can't see that, but it's flat. See, it lies in a plane. What if we have 4? No, not yet. 4. 3 still. Okay. Sorry, got ahead of myself. Here's formaldehyde. Lewis structure. So we look at the central atom, and there are 3 groups. 3 groups arrange themselves in a trigonal planar arrangement. That's redundant. What happens here, though, is that these bond angles are not all the same. They're not all 120. And the reason for that is the oxygen and the double bond here are a little bulkier. They're a little more repulsive than the single bonds. And so the hydrogens are willing to get a little closer to each other to get a little further away from oxygen because they hate him more than they hate each other. I am not going to ask you to know specific angles for these guys, but I would like you to be able to predict that this is going to be larger than 120 and that this one's going to be less than 120 because this is bulkier and more repulsive. Okay? Now with the 4. This becomes 3-dimensional now instead of 2-dimensional, harder to draw pictures of. So here we have photographs of balloons like I've been playing with here, but the YouTube people can't see those. So what the balloons are representing are the electron groups. They're not representing the atoms, they're representing the groups. So here's 2, they're going to be opposite. Here's 3, they make a triangle. And then let's see what happens when we put in a 4th one.
You cheat for after one.
No. You guys knew I was full of hot air, right? Now you got proof.
highest?
the other ones?
If it
No,
was real
it's
high,
not that high.
I was gonna say, if it's real high, then it'll rise, right?
Yeah, it would. It's not that hot. It's just warmer than room temperature. Okay. This is actually much trickier than it looks.
Must be a great time at a birthday party.
I'm so tired of birthday parties.
6 kids.
It's like- So here's a word of advice. When you have your first kid, you're gonna wanna throw this huge party for their first birthday. Restrain yourself, okay? Do not set precedents that you don't want to do every year. Now, maybe the first year you can get away with it, but once they're old enough to remember what you did last year, you're in trouble. Okay, so what this has done by,
One question about kids and birthdays.
what,
How effectively have you broken up the birthdays of your children? Like, do you have like 3 in 1 month?
we have birthday seasons. There's 2 in October, that's football season, so they often don't get parties until like 6 months later. And then there's 2 in January, 2 days apart, but there's 16 years in 2 days, so that's okay. And then February and March. And I'm in March, and my mother-in-law's in February, and my husband's in September, so we just finished birthday season, yes! We're good till October.
September, what about you?
Well, yeah,
When you're an adult,
yeah, it doesn't matter. Okay, anyway.
Let's celebrate birthdays.
Birthdays are overrated. We'd just rather not talk about them anymore. Okay, so what happens here is I added this balloon, and it pushes these guys down a little bit. Can you see that? So it's like symmetrical. It's a really weird shape, isn't it? It's not something we run into much in everyday life. It's called a tetrahedron. So if you remember from geometry, a polyhedron is a many-sided thing, right? Tetrahedron has 4 sides. So 1, 2, 3 on the back and 1 on the bottom, 4 sides. Each side is a triangle connecting the points of the balloons or whatever. So it makes a tetrahedron. Now it's in 3 dimensions around a sphere, if you will. We're taking that and dividing it into 4, and I honestly do not remember how to do that, if I ever knew. It's 109.5 degrees. I want you to remember that number, 109.5. So 4 things distributed in 3-dimensional space, 109.5 degrees for their angles. So a molecule like methane, here's its Lewis structure. We look at the central atom. There are 4 single bonds. That's 4 electron groups. We think about the balloons and how they got away from each other. And this is a representation of that tetrahedral geometry. Yes? Can I have that?
yeah, sorry.
Sorry. Okay, so here is the ball and stick model of that. That's a tetrahedron. It's 4 things arranged symmetrically in space. I have some model kits, and if you want to play around with these during lab today, I'd encourage you to do that. So the Lewis structure looks like it's flat and would have 90-degree angles. But the actual molecule looks like this and has 109.5-degree angles. Any questions? What if we put in another one?
No.
Yeah,
Why?
because these things actually exist. Ask God. At first, when I bought these balloons yesterday, I was disappointed that they were kind of small, but now I'm thankful.
Oh.
Wow, that one's so good. It's the incredible shrinking balloon. That's what you get for shopping at Smart and Final.
Better than the dollar store.
probably better than the dollar store. And closer. Because we're supposed to have balloons in the stockroom, but ours are not. Okay. So here we go. Going in, another balloon. There have been semesters where I forgot that I was going to do this until the last minute and ended up using things like hair ponytail holders to hold these together. That was really interesting. Okay, so now what we've got going on here, being a little squirrely, we've got 3 around the middle and 1 on the top and 1 on the bottom. So this pink one I think of as the little girl's head, right? And these are her feet, and this is her tutu, right? She's a ballerina. Earring. You guys aren't impressed, that's okay. Okay, so this is the head and the feet. So this is her body, and then this is like a tutu. These are called the equatorial positions, like around the equator of the Earth. And these are axial, like the North Pole and the South Pole. For this geometry, those distinctions are important because the bond angles are not all the same. You can't take 5 things and put them evenly distributed around a sphere. Seems like it should be possible, but it isn't. So what we have is a 90-degree angle between the axial position and an equatorial position, but between the equatorials, it's 120. So this is called a trigonal bipyramid because it's 2 triangular pyramids stuck together, or 2 tetrahedrons, sort of. Okay, so we've got 3 groups lying in a plane, and the other are above and below. Questions? And then one more. Octahedral. What color don't we have? This is more than Chem 3A, yes. Chem 3A, we took you to 4. We stopped. Ooh, that's a tough one. Could have just used the ones I had yesterday, but that'd be no fun. You gotta get the full effect of seeing them come together. Oh, by the way, this is a ball and stick model of the trigonal bipyramid. Yeah, that's the octahedral model.
You get these on like a house on Amazon.
Yeah, you can buy them on Amazon. They're really useful. And they're just kind of fun, too. You want to have a nerdy toy on your desk at work or something. Okay, so now we've got an octahedron.
An extra more tutu.
Yeah, so it's just a fuller tutu. If the pink is her head and the yellow is her legs again, now her tutu has more fluff in it. Okay? Pretty dancer. So this is the model. Kind of looks like a cartoon satellite or something orbiting, right? Okay, so you can spin it around like that. I want you to have a visual of these because that's the best way to be able to solve the problems, answer the questions. You got to see the balloons in your mind. Okay? So something like sulfur hexafluoride. Sulfur, remember, is one of those period 3 elements that can expand its octet. And so it's actually got 12 electrons instead of 8. Makes an octahedral, and this is the geometric representation. Here's the ball and stick model. By throwing one more into the equatorial positions, now all the angles are the same. They're all 90 degrees. Okay, those are the 5 basic shapes. Any questions?
find out how does the 5 find?
So we've got linear. So that's with 3 groups. They make a line. We've got trigonal planar, a flat triangle. That's with 3 groups. 4 groups, we get a tetrahedron, tetrahedral geometry. Oh, that's the actual picture. We throw another one in there, we get trigonal bipyramid. So that's different than trigonal planar. And then we get octahedral. So let's do an example. Determine the molecular geometry of carbon tetrachloride. You have to start with the Lewis structure. That's why we did Lewis structures before we did this. So carbon in the middle, and the chlorines around. Ooh, I didn't space that out very well. How many total valence electrons? 4 chlorines, they're each what? 7. So 4 times 7. And how many for carbon? 4. So this is 32. So I've already got 2, 4, 6, 8 for the bonds. 10, 12, 14, 16, 18, 20, 24. 2, 4, 6, 8. 10.
So, yeah, never mind. Just keep going.
Okay.
You got it. I was just, yeah.
You're just messing with me. Yeah. You were doing it on purpose, right?
He is a younger brother.
I'm the middle child.
Oh.
Well,
Worse.
that you are a younger brother then, and an older brother. That's a terrible combination. Okay, there it is. Regardless of counting, that's what it is. To find the molecular geometry, we're going to look at the central atom and ask ourselves how many groups? 4 groups. 4 balloons do a tetrahedron. So it's going to be a tetrahedral geometry. Any questions? Pardon me?
Linear is 2 groups.
Linear's 2.